So we're going to be solving applied related rates problems that involve trigonometric differentiation. We're going to look at two examples. Two sides of a triangle have lengths of 20 and 35. They could be feet or inches or centimeters or meters or whatever. And the angle between the sides is decreasing at a particular rate. It happens to be decreasing at pi over 80 rads per second. And then there's the question. What is the rate at which the third side's length is changing at a particular point in time? So we're going to start off by drawing this, and I'm going to draw these two sides connected together so that one of the sides is horizontal. It will just make it easier for us to see what's going on. And whether I choose to draw this first side as being the 35 or the 20, it doesn't matter. I'm going to say it's going to be 35. And we're going to actually put 35 on here because it is a fixed length. And I'll talk about this seems like a very contrived situation, but there's a real application that's identical to this that I'll talk about in a second. And connected to this is another length, and it's equal to 20. And I don't know, I can get out a ruler and kind of estimate that. Let's see, 35. I would say 20 might be about like that. You certainly don't have to do this. So that's 35. Oh, I'm choosing a lousy scale here. It doesn't matter. I'll go with 10. And again, you don't have to do this. I don't even know why I'm doing it, but I started doing it, so I'm going to finish it. 35 over 20 is that. So 10 divided by 1 point. I'm just working out a ratio. I should be drawing this one about 5 point something centimeters long. Yeah, it was a little long. Okay, so that's what we're looking at. That doesn't look right, does it? I guess it does. I'm just spatially impaired, I guess. I don't know. Anyway, there you go. And then we have a third side, and I'm going to draw the third side with a different color. I'm going to draw it pretty thin. And you can imagine what's going on here is these two red sides are, the angle is decreasing, and you can imagine that third side as being like a piece of elastic. So it's maintaining the triangular shape. The real application for this is when you have different moving parts on a crane. There's lots of other applications. But if you have different moving parts on a crane and one arm of the crane is rotating at a certain angular rate of change due to the gears that are moving it, then there's a support cable that connects the two ends of these pieces of metal, and you need to be reeling in that support cable at the right rate, otherwise the crane loses structural integrity and you have a disaster. So there are all kinds of situations where something like this would be needed. This is not just a contrived situation. So what do we know? We know there's an angle here, and we're told that d theta dt is equal to negative pi over 80. And that's in rads per second. And I'm going to come back to that rads per second importance in a bit. And we want to find out the rate of change of this other length, so we need to call this other length something. I'm just going to call it L for length. So we need to find dL dt. And the problem now becomes, what's the connection between L and theta? Because to go way back, not that long ago, but a few weeks ago, maybe closer to 6 weeks ago, what we need when we solve a related rates problem, is a relation between the variables whose rates of change we know or want to find. And we know d theta dt, so theta is one of those variables. And we want to find dL dt, so L is the other variable. So we need a formula relating theta and L. And I'm going to give everybody a minute to ponder that. And if you happen to know what the relation between those two variables is, just put your hand up and down so that I know that you know. Okay. You learn some things in Math 20 about trigonometry that are just kind of standalone things that you learn about and then you forget about. Craig?
It's the cosine law.
It's the cosine law. Now, you may not remember the cosine law, and if you're wondering what I'm looking for, I photocopied a basic trigonometry formula sheet for you, and I must have left it on the photocopier. It's the cosine law. The third side of any triangle can be defined or found if you know the other two sides and the angle between them. Now, we don't know the angle between them, but the relation is the same. There's a relationship between the missing side and two fixed sides with an angle between them. And the relation is that L squared will be equal to 20 squared plus 35 squared minus 2 times 20 times 35 times the cosine of the angle. Does that ring a bell? Like that it might be a squared equals b squared plus c squared minus 2bc cos a. I don't remember the version I have on the formula sheet, which I'll get to you today. And really, once you stumble onto this or figure this out, this is pretty simple. I want to say I'm not too worried about what 20 squared plus 35 squared is, but I suspect we are going to need to know later, so we might as well calculate it now. The reason why I'm not too concerned about it is the derivative of it is 0. But again, I think we're going to need it a little later. So 1625. L squared equals 1625 minus 1400 cos theta is my result, and I see some nods, so I just went 2 times 35 is 70, 70 times 20 is 1400. And now we can differentiate, and we're not going to worry about solving for L. Why would you do that? If you solve for L first, then you're going to have to differentiate something that's a square root of a trigonometric. Instead, just differentiate. 2L dl dt. Remember, I want to go back here and just show this to you. For related rates, we're always differentiating with respect to time because we have rates of change with respect to time. This is where we get the dl dt and d theta dt from. As we say, let's introduce time into the equation. Equals 1400 sine theta d theta dt. And I'll just break that down for you. The derivative of 1625 is 0 because 1625 is a constant. The derivative of cosine of theta is negative sine theta d theta dt. So, I mean, I could have written instead of that negative 1400 times negative sine theta times d theta dt. I could have done that. But negative times negative is positive. And now we're ready to go. But, no buts. We're ready to go. We want to find dl dt, so we need to know d theta dt, which we do know. D theta dt is negative pi over 80 rads per second. We need to know sine of theta. And I see a couple of you training your eyes up towards the ceiling. I hope you're thinking of the unit circle when you're doing that. Because theta is pi over 6. And there's nothing wrong with you figuring out what sine of pi over 6 is and putting the number in. I'm just going to write sine of pi over 6 in here, which, by the way, sine of pi over 6 is 1 over 2. And then we also have over, this is going to be for dl dt, we also have over 2l. You don't need to write L. You can just put over 2, and we're going to figure out what L is. But we need to just kind of pull over and do some calculations here. The formula, I believe, was L squared equals 1625 minus 1400 cos theta. Am I right on that? Okay. So that means that L is equal to the square root of 1625 minus 1400 cosine pi over 6 cosine of pi over 6 is root 3 over 2. And if I multiply root 3 over 2 by 1400, I get 700 root 3. I better just write that out. L will be equal to 1625 minus 1400 times root 3 over 2 to the half. I don't care. You want to write square root? Write square root. And then that 1400 over the 2 reduces to 700 on the top. So L is equal to the square root of 1625 minus 700 root 3, or 1625 minus 700 root 3 to the half. One more little bit of business here. It's really too bad that these numbers on the top are not going to reduce down nicely. I think we're still going to be left with a fraction on the top. I have a 1400. I'm multiplying by sine of pi over 6, which is 1 over 2. I'm multiplying by negative pi over 80. So what I have on the top with these numbers, not the pi or the negative, it's 35 quarters, I believe. And I'm seeing some people start to nod. So that means this whole top, being a little sloppy here in how I'm presenting this, but this whole top is negative 35 pi over 4, so I can just throw the 4 on the bottom. And get, if you're interested in an exact value, negative 35 pi over 8 times whatever this is. And don't waste a moment of synaptic nerve activity trying to simplify that radical. It doesn't simplify because it's the square root of a difference. There's no rule for that. Let's run this through the calculator. Let's find out what this is equal to. I'm not doing it from the bottom line. I'm doing it from one line up just to double check to make sure I've simplified it correctly. Negative pi times the 700 divided by 80, and I got to divide that by 2. Oh, I hate being in this mode. Oh, what a crap show. See, I do all that typing, and then I look up there, and I can't see what I've typed. Negative 700 pi over 80, that's right, divided by that 2, divided by the square root of 1625 minus 700 root 3. This is what I'm getting. Did anybody calculate it from my final line down here? and you're getting the same thing. Okay, that's just my way of checking to make sure that what we've written is correct. So it's about negative 0.67 units per second. You know, if those lengths were in meters, then it would be meters per second. If they were in inches, inches per second. What's interesting here, and we don't have time to get into why, it's an interesting thing if you want to think about it, is you have to use radians. There's something natural about radians that they will work and degrees won't. And this goes beyond the reason we use radians for applications in Math 30. It's a different reason. See, if you were to say, oh, I'm going to use 30 degrees instead of pi over 6, that's all fine, because you're still going to have sine of 30 degrees here, which is 1/2. But if you figure out how many degrees pi over 80 radians is, it will be a different number. And when you put the number in here, you will not get this answer, and this is the correct answer. Your rates of change have to be in radians per unit time. It just doesn't work with degrees. And you can rationalize that by saying the reason is, in a very general sense, radians are connected to a circle. And ultimately, trigonometry is about rotations. A degree is an arbitrary division of a circle. Somebody said, oh, let's put 360 in a circle. Anyway, any questions with the work we did here? The next example is probably a more important one. It's something that my computer's all jammed up. It's something that is probably more of a typical problem, and there's a little bit more math involved. There we go. So we have a beacon. It's a rotating beacon. I'll explain to you what that means in a second. We have a beacon that is located 450 meters perpendicularly measured away from a shore. So we'll just say the shore is over here. So there's water to the left of that. There's land or a beach to the right. And the perpendicular distance to the location of the beacon is 450 meters. And whatever we decide to do in solving this problem, which we haven't even read yet, we can put that 450 there. That distance is fixed. And what the beacon is basically a light source. But it's a beam of light. Maybe the rotating beam of light on the top of a lighthouse, where you've seen in movies probably, or maybe in person if you're lucky, that beam of light sweeps around. And it's not lighting up everything because it's really kind of a tight beam. It's just lighting up a spot in the distance. And I'm going to draw that beam of light this way. And what is variable here, what we cannot put a number to, is the distance from that spot of light on the shore. Come on. From the distance to the spot of light on the shore to this point, that distance is variable. We can call it d. And the reason why I've introduced that variable is, I already know what the question is going to ask. The question is going to ask, how rapidly is that spot of light moving along the shore? And if I want to know how quickly this beam of light is moving along the shore, and let's assume the beam is rotating from your perspective clockwise. So it's this spot of light that I'm indicating right here is currently on its way down. That distance is changing. That distance I've labeled d is changing. And how quickly it's changing is how fast that dot's moving at that point in time. So now let's finish reading the question. It says, how fast is the beam moving along the shore? Okay, so that's d dt. And I did something that I tell you, don't do that. I'm choosing d as a variable, but so what? How fast is that beam moving along the shore at a particular point in time? I want you to understand that there's two questions here. How fast is the beam moving along the shore at this instant? And then how fast is it moving along the shore at this instant? There's two questions here. You know how all related rates say, determine the rate of change of this when that? Well, that are those highlighted things. So we don't have to worry about that. This beam of light is rotating at 4 revs per minute. So we're trying to find this, and we know, or I know, and maybe you know, but we have to figure out from it what the rate of change of the angle is. It makes 4 revolutions per minute. So what are we going to do with that? We want rads per minute. We don't have to go rads per second. You can go rads per minute. Any idea what we can do there? Well, how many radians is a full revolution? 2 pi. So this is 8 pi rads per minute. The rest of this question is not difficult except for one thing. I mean, what's the relationship between d and theta? Because these are the variables, right? What's the relationship between d and theta? Well, it's a tangent function. Tangent of theta equals d over 450. So better yet, d equals 450 tan theta. It's a pretty simple trigonometric relation. It's a function as well, but I'm just calling it a relation. So we've set up with my help what's going on in this question so that you see it in the future, you know what's going on. I've made my list of rates of change that we want to know or do know. Based on that, I've come up with my formula. Now I'm going to differentiate. I'm going to differentiate everything, both sides of this equation with respect to time. And get d dt equals 450 secant squared of theta d theta dt. I think. Okay. So here's this isn't difficult, but students want to do something here that you, not only do you not have to do, you don't want to do. You do not want to find theta, okay? So we have two problems here. Find d theta dt when d equals, I'm going to do the second one first. When d is equal to 200. They're saying at this point in time, this is 200. We don't want to add that to the diagram because the diagram is variable, but I'm just saying that's what we're looking at. So the biggest mistake is starting to do this. You go d dt equals 450. We're going to put 8 pi in here. And you go, oh, I need to know theta. No, you don't. And you don't want to find theta. Because as soon as you find theta, you're going to be going inverse something and you're going to get decimals. We want exact values. What you want to do instead is find secant of theta. So now we're talking about this point in time where this is 450 and this is 200. What we want to do is put in secant of theta. Now, secant is the reciprocal of cos. And we revert back to SOHCAHTOA here. We're not talking unit circle or anything. In terms of theta, this is the adjacent side, and this is the hypotenuse. So what's going to go in here will be the hypotenuse over the adjacent side, because I hope you understand that secant squared is this in brackets squared. Because secant is the reciprocal of cos, cos is adjacent over hypotenuse, so I flip it over to get hypotenuse over adjacent. I need to find the hypotenuse. It's going to be the square root of 450 squared plus 200 squared. So, 450 squared plus 200 squared. And I want to say all the time, but there's going to be exceptions. Most of the time, you're going to be in this position where you don't care about simplifying this number. It's the square root of 242, 500. Now, why don't we care about simplifying that? Because this is squared. So who cares? It's all going to become rational in a second, except for the 8 pi, of course. So the other thing to note is we're going to get 242, 500 after squaring the square root. And we're going to have over 450 because the 450 in this denominator is squared, which gives us 450 times 450, but we're multiplying by a 450 up top here, and then it's 8 pi. I have every faith that you can simplify 242,500 times 8 over 450. I don't care. Let's get a decimal answer. I mean, if you wanted to, you could write the answer as, it's not even doing it. It'll be some number over 9 pi. I don't care. It's about 13,543 meters per minute. If you want to divide that by 60 to find out how many meters per second it is, we could do that. It's about 225 meters per second, about 2 football fields per second. Any questions with that part, which is the second question asked here? All right, what if then we want to find d theta dt, or d dt rather, when d is what? Well, that one says when the beam is at the nearest point, which means the beam is there. Which means the rotation angle at that point, or the angle in the triangle, is 0. The cosine of 0 is 1. The reciprocal of cos is secant, which would therefore be 1. Are you with me on that? We're dealing with this equation right here. I'm cheating my space out a bit here. But it's going to be 450 times 1 squared times 8 pi. That's going to be at 3,600 pi, I think. And it's why I wanted to start with the other one first. It makes more sense to learn it with a triangle. And I really should change the order in which I ask these. Anyway, 450, 450 multiplied by 8. Will give you 3,600 pi. So this time it's about 11,310 meters per minute. And if you divide by 60, of course, it's about 188 meters per second. Slower because it's closer to the point. As it gets further away, a small change in the angle produces an immense change in the distance. I think the biggest thing is not going overboard and finding values of angles here. And by the way, some people take away something from what I've said about this, meaning you want exact values. And this is not the exact value. This is not acceptable. I know it's technically right, but this is not what we're after. All right, well, so how would you find the angle? You'd go inverse sine of 200 over 450. And then what do you have to do with that? Take the secant of that and then square it. That's no good. Don't do this. Do you get what this person has done? They told me how they would calculate it in decimal form by showing me calculator buttons. It's like me saying, show your calculations, and you draw a picture of your calculator. That's not what I'm asking, okay? Get my drift? Okay. Do it the way I've shown you. There we go. There's numerous types of problems here. Your job is to read the problem, identify the rates of change. One will always be a d theta dt that you either want to find or you know. Identify the other rate of change that you care about, come up with a trigonometric expression connecting them, and you differentiate and you do the same stuff we would do with any other related rates problem. I've added some extra ones in here just because, and same thing as always, even 8 to 14 is a lot. Expand your mind a bit. Try some that look a little more challenging once you get the hang of it. I'm going to grab those sheets. They have SOHCAHTOA on there, the sine law and the cosine law. So I'll give that to you as well, and you would have that for exams.